Hi, welcome. Here is Tsai-Shien. This video presents our CVPR 2026 paper named Omni-Attribute, Open Vocabulary Attribute Encoder for Visual Concept Personalization. Our motivation is the copy-paste artifacts, which commonly show up in recent video personalization models like Phantom, Movie Weaver, and Bindweave. They not only refer the target object's identity, but also copy other attributes from the image. For example, facial expressions, clothing, and even the background. To address this, we propose an entirely new thinking pattern. Can we prevent this information leakage at the encoder stage? We believe the core issue behind copy-paste artifacts is that existing image encoders, like Clip or Dino, encode all information from an image into a single set of image features. This makes different attributes become mixed up, making them very difficult to disentangle. So we raised a question. Can we learn an attribute encoder that only extracts the information of the user's specified attributes? To achieve this, we proposed a novel open vocabulary image attribute encoder. Our attribute encoder aims to learn attribute-level image representations. Here's an example. A user can provide an input image, like Mona Lisa, together with a textual attribute description, like person identity. The attribute embeddings from our encoder will focus specifically on the person identity information in the image. So when the decoder generates a woman riding a bicycle in a park, the output result only inherits the person identity from the input image, while everything else is entirely controlled by the text input. If we input the same image and the same prompt, but change the attribute to clothing, then the output image will only inherit the clothing from the input image. What's even more interesting is that we found our attribute embeddings can be assembled like Lego. We can fuse different attributes from different images into one single coherent image. If you're interested, feel free to check out the project webpage and try it out for yourself. Also, thanks to this kind of composable nature, we are able to achieve attribute-level compositional image generation. This enables highly creative personalization. So how did we learn this attribute encoder? First, let's introduce our training data set. We train our attribute encoder through semantic connections between image pairs. Each of our training samples is a pair of semantically related images, for example, these two dog images. To establish the connection between a pair of images, we use vision language models to perform attribute-level annotation. This includes positive attributes, which are the attributes shared between these two images, such as the dog's identity or the background, and also negative attributes, which are the attributes that distinguish these two images, such as the dog's pose, the camera angle, or the lighting conditions. This pairing structure allows us to teach the encoder which visual concepts should be preserved and which should be suppressed. So how do we supervise the training of the attribute encoder? This attribute encoder has two goals. First, the embeddings need to capture sufficient information to ensure high-fidelity reconstruction of the target attributes. Second, the embeddings need to remove irrelevant information from other attributes. To achieve both of them simultaneously, we designed a dual-objective attribute-level representation learning framework. First, we designed a generation loss, as shown in the upper half of this figure. We randomly select one image from the image pair as the reference image and the other as the ground truth image. This generative loss ensures that the extracted attribute embeddings can faithfully reconstruct all positive attributes shared between the two images. To achieve the second objective, we designed a contrastive loss, as shown in the lower half of this figure. We attract the features of positive attributes closer together while repelling the features of negative attributes apart. This contrastive loss ensures that the extracted attribute embeddings only have information relevant to the input attribute. Because even for the same image pair, their attribute embeddings will sometimes be attracted closer and sometimes repelled apart, depending on the input attribute. Okay, regarding the model architecture, we use a multimodal large language model as the foundation for our attribute encoder because of two reasons. First, the attribute encoder needs to jointly process both image and text inputs. Second, the attribute encoder needs to have strong vision language prior knowledge to support our attribute disentanglement task. To achieve both of them, our attribute encoder is an MLLM equipped with LoRa fine-tuning modules, followed by a fully trainable connector. Meanwhile, our decoder is a pre-trained and frozen image generator. We use Flux here, equipped with an IP adapter to enable attribute personalization. So that's how we built and trained our attribute encoder. Here, we compare Omni-Attribute with existing attribute personalization models. We show comparisons across 11 attributes, including 3 concrete object attributes on the left and 8 abstract concept attributes on the right. We compare against 2 groups of models. The top 3 are image encoders, and the bottom 3 are image editing. In both the qualitative comparison on the left and the quantitative evaluation on the right, we can see that Omni-Attribute better extracts the target attribute from the image and coherently put it into the context of the text prompt. So far, we've discussed how to achieve single attribute personalization. But how do we combine multiple attributes together? We actually achieve this through an extended form of classifier-free guidance, or CFG. This idea is inspired by a work from ECCV 2022 called composable diffusion. In the original CFG, we calculate the difference between the conditional prediction and the unconditional prediction to get a conditional score direction. Composable diffusion found that multiple input conditions can be fused together through a linear combination of these conditional score directions. We follow this approach and extend the formula to our flow matching model. Specifically, for each image attribute condition, we compute its conditional flow. Then we achieve multi-attribute composition by computing a linear combination of these individual conditional flow fields. Through the capability of this attribute composition, we can achieve many interesting applications. For example, advertisement image synthesis. We can progressively fuse attributes into an image. Or hairstyle customization. We can apply different hairstyles to the same person. Or storytelling. We can narrate a character's journey exploring the world. Finally, we can also produce highly creative content generation. That's all about Omni-Attribute. We thank you for watching the video. Hope to see you soon in another video.